Hello everyone, and welcome to our first lecture on an introduction to kinetic molecular theory. So in this video, our goal will be to describe the 6 assumptions of kinetic molecular theory. And this will give us the background to analyze the behavior of gases, and especially ideal gases. So to start, let's introduce kinetic molecular theory. So kinetic molecular theory, which is also sometimes abbreviated, and as we will do here, KMT, is a model or way of describing the world. So it's a model that describes the behavior of gases. And so what it's going to do is it's going to help us understand what is happening in a gas, both at the molecular scale, but also in a way that we can understand what happens to a gas or the behavior of gases at a macroscopic or human level. So KMT has six central assumptions. And we're going to go through each of the assumptions one by one. And then at the end, we'll kind of try to bring it all together. So the first assumption of KMT is that KMT says that gases are made up of hard spheres that so hard spheres or hard particles, and a large number of them that are in constant and keyword here is constant random motion. So the particles will never stop moving, essentially. And then the motion of these particles will be essentially random, or at the speeds at which they're going. Essentially, what this is saying is it's saying that gas particles or gas molecules are pool balls or billiard balls. And to help us remember that, let's go ahead, let's draw ourselves a little, maybe like a 1 ball per se. So 1, it's got that little white, do a little 1 here to help us see that. And then we can fill in the rest. So basically, assumption number 1 says that we can think of gases as consisting of a really, really, really large number of particles. Remember that when you breathe in, just one breath holds 1,000 trillion molecules, or these little hard spheres that we're going to think of them as. And essentially, if we were to zoom in, the way that these particles act is a lot like a billiard ball or a pool ball on a pool table. So that's assumption number 1. Assumption number 2 says the following. It says that these particles, these billiard balls, which are in constant motion and randomly moving around, these particles move in a straight line until they run into another particle, or they hit the wall. So essentially what assumption number 2 is telling us is that they will just go in a straight line until they hit something. And that's basically it. So what we can do is we can draw our yellow billiard ball. It's going to go in a straight line, boom, until maybe it hits, oh, I don't know, another billiard ball. Or alternatively, it's going to go in a straight line until it hits the wall of a container. So that's it. So the balls can hit two things. They can hit each other or they can hit the wall, and they're going to move in a straight line until they hit something. They're going to collide off, and then they'll move in a straight line in a new direction. Assumption number 3, important to know. So that's assumption number 1 and number 2. So far we have gases are made up of little hard spheres, and that those hard spheres move in straight lines until they hit something. When they hit something, they'll change direction. Assumption number 3 is that the size of the particles, or the size of our gas particles, are insignificant. Insignificant compared to the size of the container. And we'll just finish writing this, and then we'll go through what that means. Basically, what this says is that most of the volume of a gas is just empty space. So most of the, like if we had a balloon, right, the balloon takes up a given volume. Most of the balloon will be empty. And so there will still be a really large number of particles inside that balloon. Or like when you take a breath, there's still a really large number of particles inside your lungs, but there's actually just mostly empty space in between. All right, so we've got the gas particles are billiard balls. They move in straight lines, and the billiard balls are really, really, really small compared to the size of the container. That brings us to number 4. And number 4, assumption number 4 is this. And it's a little bit confusing, so we'll go over what this is after we write it. It says that there are no interactions or forces of attraction. We shouldn't say no interactions. Let's say there are no forces of attraction between particles and between particles in the wall. So what assumption number 4 is saying is essentially that the particles, when they collide, there's no stickiness to that collision, or that there's nothing that wants to bring those particles together. We will see that this is probably one of the weakest assumptions of KMT, and in fact, there would be no such thing as a liquid or a solid if this was true. But as a first approximation for most gases, this assumption that there's nothing that wants to make those molecules come together is a pretty good one. And for some gases, like for example helium, it's a really good one until we get to some very extremely low temperatures. But what we can say is that the motion of the particles, or the way that the particles are moving, is more significant than any force of attraction between the particles. And this brings us to point number 5, and again, we're going to write point number 5, and then we'll go through what point number 5 means, is that all collisions are perfectly elastic. And what that means, you might recall from physics last year, is that no energy is lost between collisions. And that's essentially what that means. Let's try to illustrate this quickly with an example, because I think talking about elastic and inelastic collisions, we might get a little bit confused, but basically it means that there's going to be no momentum lost during a collision, or there's no energy lost during a collision. But I think a great example of this might be a bouncy ball. So with a typical bouncy ball, let's draw a little floor here in our bouncy ball. When we drop a bouncy ball, or maybe throw it at the floor, what we will see is that initially it will hit the ground, and then it will bounce up. And when it bounces up, it will bounce up a little bit. It won't bounce quite as high as it initially did, because what's happening is it's losing energy every bounce. And we can kind of draw this. In a good bouncy ball, maybe you get 3 or 4 bounces before it kind of dies out. And this is what we call inelastic collision. And in an inelastic collision, what that means is that energy is lost every time the bouncy ball hits the floor, and that eventually the ball will stop bouncing. In an elastic collision, though, we can pretend that we have the most perfect bouncy ball. So again, we're going to start with our bouncy ball. It's going to start up here. But what is going to happen when we drop it again, this is an elastic collision, not an inelastic, but a elastic collision, is that it's always going to return back to the height at which it started. And it will do this indefinitely. And we'll just draw another couple balls here. Boom and boom. And so this, in this case, is an elastic collision. And there's no energy being lost every time the ball hits the floor. Just like in our gas, there's no energy being lost every time two particles of our gas collide. So that one's it's important for issues of like perpetual motion or kind of interesting things there. But for our purposes, we can kind of just leave it as is. All right, so the last point we need to bring up, or the last assumption of kinetic molecular theory, and this isn't really just an assumption of kinetic molecular theory, it's an assumption of most thermodynamics as well at this point. It is this. And it's probably one of the most important points that we'll have all year in terms of really thinking about the motion of molecules within a substance. And it says this. It says the kinetic energy of a collection of particles, so a large collection of particles, and I shouldn't say just the kinetic energy, I forgot to write a word here. It's a very important word. It's the average kinetic energy. So let's make sure we go back and we say that for sure. The average kinetic energy of a collection of particles depends only on the temperature. And let's really emphasize this only point, because I think it's really something that we need to emphasize. So before we break this down, let's just make sure briefly that we know what kinetic energy is. So kinetic energy is the energy of motion, roughly speaking. Actually, I think pretty accurately speaking, but is the energy of motion. So it describes how much energy something that is moving has. You might remember we could represent it using an equation, and that equation tells us that kinetic energy has, two parts. The first part, so we're going to write the equation Ke equals 1/2, and that 1/2 is from an artifact of some interesting calculus, but we won't go too far into that. 1/2 mv squared. So the m means that this kinetic energy depends on the mass of the particle, and the v indicates that kinetic energy depends on velocity. And in fact, it doesn't just depend on velocity, it depends on velocity squared. So what it's basically saying, this point number 6 is saying, is that the higher the temperature, the temp, the faster, roughly speaking, the particles will move. And that's a really big result, because it says that the only way we can change how fast those particles are moving is by changing the temperature. If we want the particles to speed up, assuming that they have the same mass, we want the particles to speed up, we have to increase the temperature. If we want the particles to slow down, that means we have to decrease the temperature. And so what it says is the kinetic energy is actually directly proportional to the temperature. Again, that is a really big result, and it's really going to help us kind of understand a lot of what's happening at that molecular level, because this really determines how fast those particles are moving. And so just to kind of summarize or wrap up, the really big idea from today, and this is the big idea, and it's a really big idea, is that these 6 rules describe almost all ideal gas behavior. So in the case of our baking soda plus vinegar reaction, these 6 rules help us describe why the pressure increases. If we wanted to know why a balloon that we put in the freezer will shrink, hey, we can look to these 6 ideas. If we want to know why a balloon that we put in some hot water will expand, we can look to these 6 ideas. If we want to know why the pressure inside of an Instapot is increased, hey, again, we can look to these 6 rules that help us out. So what we're going to do is we're going to end the lecture here for today, and we'll look at examples of how these 6 rules can describe gas phenomena in a separate video. So thank you very much, and we'll see you on the flip side.